Let's begin. So, good morning, good afternoon, good evening, everyone, and welcome to the next set of tinyML talks. This is tinyML Talk India, and today we are going to have a discussion or a topic on tinyRadar, millimeter wave radar-based human activity classification for edge computing. And our presenter is Radha Agarwal from Indian Institute of Science, Bangalore. So before we go on to the talks, we must thank our sponsors, Analog Devices, Aeon Devices, ARM, Deep Light, Edge Impulse, EMSA, Photahub, Greenwaves Technologies, Gravity, HOTG, mmWave, Item RS, Clicker Tech, Latent AI, Nota AI, NXP, Prophecy, Kixo, Qualcomm, Reality AI, Rixen Technology, Renaissance, SAP, Seed, SensiML, Silicon Labs, Sony Semiconductor Solutions Corporation, ST, Stream Analyze, Synaptics, Synsense, Syntiate, without whom these talks would have been not possible. So our next tinyML Trailblazer series is on June 7th, that is 2 days from tomorrow at 8 a.m. PDT. And we got success stories with Mauna El-Khatib, CEO, CTO, and co-founder of Aeon Devices Incorporations. So register now for get the secret sauce of the success stories, right? And we encourage to join the meetup group, which is rich and growing from the last few years. And tinyML, as you know, is the hot topic out there. So if you don't want to miss out anything about tinyML, better join these groups out there. And also, all these talks have been recorded and been published on the tinyML YouTube channel. So it's best to subscribe so that you don't miss out on any updates, including this video, which will be uploaded in some time onto this channel. So, and our next tinyML talk is on June 8th. It is Danilo Pau, ST Microelectronics, from ST Microelectronics. It's a tinyML meetup Italia with so it would be, webcast would start at 8 a.m. Pacific time. And if you're interested in presenting, reach out at talks@tinyml.org, and we can plan a talk, tinyML talk regarding your tinyML organization or any other foundings. Let me introduce our speaker today, and it is Radha Agarwal, who's a master's student at the Department of Electronic System Engineering, Indian Institute of Science, Bangalore. She is a Texas Instruments scholar working on mmWave radar project in Neuronics Lab, ISC, under the guidance of Dr. Chetan Singh Thakur. So she's done several projects involving machine learning, embedded systems, and digital design using FPGA. So field of interest include applications of machine learning and embedded systems. And in 2020, she was awarded the prestigious Governor Silver Medal for her academic performance in BTech. So Radha, take it away.
Thanks, Abhishek. Talk is about tinyRadar, an mmWave radar-based classification system for edge computing. So in our busy lives, we need some sort of remote surveillance system to take care of our child, elderly people living alone at home, or to detect the intrusion in restricted areas, or to take care of the patients, because there cannot be a nurse to take care of patients 24/7 to detect the alarming activities like fall or completely no activity. So in such scenarios, what if we keep camera in all these places, like in our living place, in a patient's room, etc.? Will it be surveillance or spying? Like this article says, if a camera enters into a patient's room, it will cause more harm than good. Similarly, an article published in New York Times talks about how a doorbell camera spied on people living inside the home. And imagine how bad it can be if the data goes into the bed heads. It can become a big privacy threat. Other problems associated with the camera are they get blocked if something comes in front of them, or they doesn't work in dark and foggy conditions, that is low light conditions. So thinking of all these problems, a very old and renowned technology comes to the mind, that is radar. Radar came into the picture at the time of World War II. It protects privacy since it has nothing to do with the visible light. It works on radio waves. It works in low light and all environmental conditions. But you might be wondering, how about, like, is it a good solution if we replace the camera with a radar? Like, won't it be very bulky? No, my dear friend, what we want something that is cheap, that is fast enough, works in real time quickly, that is small, and that is contactless. Like, if we'll be contactless, then we don't have to like wear it. So here comes the tinyRadar. It has one ARM Cortex-R4F MCU running at 200 MHz, one DSP running at 600 MHz, one coprocessor, that is the hardware accelerator, which gets its clocks from R4F MCU only. It has on-chip memory of 1.75 MB, and it operates in a frequency range of 60 to 64 GHz, thus providing an RF bandwidth of 4 GHz. Now, how do we process the data, point cloud data coming from the radar? Should we go for the cloud computing? No, cloud computing comes with its own disadvantages, like the latency, the issue of data theft, and connectivity issues. That is, we cannot be reliable on cloud computing if it is going to be a product in the remote areas. As I told earlier, like, why go for cloud computing if already radar is smart enough to do its job on its own? So this is our proposed system, a tinyML-based single chip solution for on-edge sensing and detection for human activities. Radar senses the target environment and gives the point cloud data. The target environment in our case is the human activity. So this is the RF front end. First, the RF front end senses the environment. This is a basic block diagram of RF front end. First, the synthesizer generates the chirp. A chirp is a signal whose frequency varies linearly with the time. Here, an up-chirp graph is shown, both the frequency time plot and the amplitude time plot. A chirp is characterized by its time duration and bandwidth and the slope. This chirp is transmitted using the transmit antenna, and receiver sees a delayed version of the transmitted chirp. At the mixer output, we get the intermediate frequency signal called IF signal. This IF signal is represented by a sinusoid, like sine 2 pi ft plus delta phi. The frequency term of this intermediate frequency signal is obtained as the difference of the frequency of the between the transmitted chirp and the received chirp. So here we can see the IF signal is a constant frequency signal whose frequency is directly proportional to the distance of the object from the radar. So by exploiting this information, we can obtain the range information of the target. And the phase term in this IF signal is equal to 4 pi delta d by lambda. And mathematically, if you put like delta d to be lambda by 4, so it comes to be pi. Lambda by 4 corresponds to 1 millimeter change in distance. So we can say that phase term in the IF signal is very sensitive to the small change in distance of the object. If an object changes by its position by lambda by 4, phase changes by 180 degrees. This information we will use later to extract the range and velocity information on the hardware. So ADC digitizes this IF signal and it must support a bandwidth of S2D max by C. After the ADC data, it is given to the processor for the further processing. I think you should control the screen. There is some latency from my end. So the next steps to extract the range information. For that, we do 1D FFT across the samples. So here is the ADC data represented. It is in the form of like samples, cross chirps, cross frames. When we do FFT across the samples, we get the range information. This step is done on the hardware accelerator present on the board. When we do FFT across the samples, this is one of the range FFT map we obtained. And this map, when plotted over across multiple frames, we get such range time map. This animation shows how the range changes as the target walks in front of the radar. Range is going from far to the near. And here we can see the location of the peaks in this spectrogram gives the range information of the object. See here, we can say the target was at around 1 meter here and at around 1 meter here, and here it was far from the peak of the spectrum. The next step after obtaining the range information is to obtain the velocity information. This step is done on the DSP C67X core present on the board. So to obtain the velocity information, as I told earlier, we extract this information from the phase of the IF signal. So that phase difference comes from the phase difference across two chirps. So here we are doing FFT across the chirp dimension to obtain one range Doppler heat map. This range Doppler map in radar literature is called as one frame. Like this animation shows, as the person walks in front of radar, how the range and velocity is changing. At center, you can imagine the velocity to be 0. It is changing to positive and to the negative as the direction of the motion is changing. Also, simultaneously, the range is changing because this is the 2D FFT plot. The peak location is approximately same in the range FFT map here, but phase differs. So from that phase information, we are extracting the velocity. The next step is, since we are concerned with the human activity, so it is best to see how the velocity of the person is changing with respect to time. For that, we do velocity time map conversion. This step is also done on the DSP present on the board. How we are doing velocity time map generation is that we do incoherent addition across the range dimension. So for one frame, we get one velocity column. When these velocity columns are stacked over multiple frames, we get one such matrix. So the summary is we get one velocity time map over multiple frames. These velocity time maps contain the time-varying frequency modulations imposed on the received signals because of human body motion. You can see this is the spectrogram for a person walking in front of the radar. So to get the, we have to set some scene parameter, we have to target some scene parameters for our application. We targeted a maximum range of around 8 meters, range resolution of 4 centimeter, which is very much possible with the radar because it offers an RF bandwidth of 4 gigahertz, maximum velocity of 4.23 meter per second, and velocity resolution of 6 centimeter per second. So to get these scene parameters, we have to set some chirp configurations in the radar. We targeted these chirp configurations. These are fed into the configuration file. And there exists trade-off between the maximum measurable range and the range resolution. A similar trade-off exists between the maximum measurable velocity and the velocity resolution, because that trade-off comes from the match of these chirp configurations. There are if we increase the chirp duration, we get final velocity resolution. But If we increase the chirp duration, we compromise on the velocity. Similarly, if we target a good slope to get fine range resolution, but then we compromise on the maximum range. So the final velocity time maps, which we obtain, and these are fed as input to the convolutional neural network for the 4 activities are shown in this slide. For jogging, you see a spectrogram has very good, is very good because jogging involves complete motion of the person, but jumping, sit up, and waving are the activities where the person is standing in front of the radar at one position, just moving his hands or leg only in Z direction, not in the XY direction. So you see here, jumping and sit up are almost similar, while waving has this artifacts because of the micro Doppler signature of the motion of the hands. Here, a big challenge comes is to collecting our own data set. Radar dataset is available online, but most of these datasets have not all the information required to make an end-to-end application, like the targeted scene parameters and the conditions in which the dataset was collected, the chirp configurations which they have set. So we collected our own human activity dataset and we have made it public. So this is a small video showing the corresponding spectrogram here. How we collected our human activity dataset is we sync the camera and radar data in time and then clip images of size 64 cross 64 from this radar spectrogram. 64 corresponds to this velocity and this other 64 corresponds to the frame. By doing this, we don't have to simulate the target environment specifically for collecting the data. We can collect the unbiased data and also the transitions. So in future, if we want to collect the data for like pets or cars or vehicles for which the target environment cannot be simulated, we can do that by syncing this camera and radar video. This is the novelty of our work, that is the convolutional neural network deployed onto the Cortex-R4F MCU using CMSIS-NN APIs. We trained our model on around 1,333 images on 7 humans and 5 classes. These 5 classes corresponds to 4 human activities and 1 no activity class that includes stationary and some random motion, like some vibrations or something like wind, etc. How are we doing this? We did 8-bit post-training quantization of the CNN architecture to get the fixed point weights and biases. This 8-bit fixed point and bias are loaded into the radar memory, and using CMSIS-NN custom APIs, we deployed the inference engine onto the Cortex-R4F MCU. Here, we have kept in mind to keep the CNN network small enough to fit into the radar memory. Here you can see it has just 3 convolutional layers and 3 max pool 2D layers, followed by 1 fully connected layer and 1 output layer, which just contains 5 nodes. 5 nodes corresponds to 4 human activity and the other class. Once we got the classification result, how are we sending it to the user? We are sending it via Bluetooth. So for that, one ESP32 module is interfaced with the radar board, and mobile application is built on the user's end. So here the BLE acts as the server and mobile application acts as the client. This works fine for around 10 to 15 meter, and depending on the target application, of course, we can change it to like Wi-Fi or BLE or some other communication module. This app is built using MIT App Inventor. This is a small demo showing like how the app works. These are the results for our application. R4F CPU utilization is around 68%, which is more because CNN network is running on it. DSP utilization is around 9% because only the signal processing algorithms are running on it. Power consumption for the inference network is around 48.64 milliwatt. We have implemented the sliding window approach in which we get the classification result after every 3 frames, where 1 frame corresponds to 70 milliseconds. So we get the classification result after every 200 milliseconds. Here you see the CNN network parameters has only memory footprint of 1.44 KB. This is because the size of the CNN network is kept small, and it offers a latency of 75 milliseconds. The velocity time map generation is done using ring buffers, so its memory footprint is also less, that is around 8.4 KBs. To test the model, we kept in mind the subject independent accuracy, because the challenge is that the application should work if the target is not present in the training data set. So we obtained a 95% testing accuracy with the 8-bit quantized CNN model and tested on 657 velocity time maps of the subject independent of the training data set. The confusion matrix for the classification model is here. Jogging is very well classified because as we see, its spectrogram is very good. There are some classification for setup because setup and jumping spectrograms are quite similar, but we are able to tell it right for 83% of the times. For waving, it is also good, like 97.6%. We have published our work in ISCAS 2022 IEEE conference. Here is a small demo to show you. Here the radar is placed behind the curtain. And now, as I told earlier in the motivation slides, it works in the dark environment as well. With a different environment, in a different environment with a different subject. So I would like to thank my professor, Dr. Chetan Singh Thakur, under whose guidance I have done this work, and also the TI mentors and Mr. Sandeep Rao and Anil Mani from Texas Instruments. And I would like to thanks to the collaborators, Satyapreet Singh Yadav and Kola Bharat, who are my colleagues here in ISC. And special thanks to Neuronics lab members for their help in dataset collection. Thank you. Thanks a lot.
Yeah, so that was a wonderful presentation, and I think we can take few questions. Okay, so Rajneesh Chauhan asks, will the microwave be harmful to humans? What are the side effects of the microwave?
So as far as we know, there are not such harmful effects of the microwaves. Yeah.
Okay.
Because it is being used in for patients in hospital environment.
Okay. Okay. So how the system behaves when there are several humans, not one human, moving in the scene? Will it produce incorrect results in this situation? Asked by Alexander Zubin.
Yeah, so for that, like this demonstration was for a single human present in front of the radar. But if multiple people are present in front of the radar, there is one more signal processing step that is to be done. That is, a tracker needs to be there, which filters out, which associates the point cloud data of the radar as per the target ID present in front of it. Because radar can also be used for localization applications. So after we associate the target point data with respect to our target, then we can generate corresponding spectrograms, and then it can be used for human activity classification. I think it will work fine for 2 and 3 persons in front of the radar.
Okay.
Because for that, radar is able to very well localize those persons. It filters out the point cloud data as per the target ID.
Okay, so is it necessary to have the radar in a certain position to identify these people together, or is it like it can be placed anywhere?
That is not a constraint. It's just that it should be in the field of view of the radar.
Okay. Okay. So when you say field of view, does it mean that if there is an obstacle in between, will that cause a wall or something? How is it a penetration problem?
By field of view, I mean the plus minus 60 degree or plus minus 45 degree, that way, in azimuth and Z direction.
All right. So Alexander again asks, can you describe why two-dimensional FFT is necessary?
Yeah, so as in my slide, I showed to extract the velocity information, we are doing that 2D FFT. Like I showed the spectrogram. If you have any particular question, like I showed in the slide, why are we doing 2D FFT to get the velocity out of it? Okay. Because the phase information of the IF signal contains that.
So will multiple radars, if you have multiple 60 Hz radar, interfere with each other if they are kept in the same room? Will that cause an issue?
For that, interference mitigation algorithms have to be deployed if there are multiple radars are there, because they all are working on the same frequency range.
Okay, and Gladwin Jobs asks, what are the challenges in getting the radar hardware configured for getting chirp data?
For getting chirp data, like normal ADC data, not the signal process one, if you mean that. So I don't see that as a big challenge, because for that there are tools available online for which you have to set your target scene parameters, like what you are targeting at this much range, this much velocity. The corresponding chirp configuration you get from those tools, you can send that CFG file to the radar, and it will give you the raw ADC data. On that, you can do signal processing on MATLAB also, if you need that.
Okay. So Raja Dev also asks whether real-time classification happens within the device or is connected to any high-end computer.
Yeah, that is the novelty of our work. We are doing inference on Cortex-R4F present on the board itself.
Okay. And let's take a final question by Uzair, who says, do you faced any challenge? Have you faced any challenges in data collection?
Yeah, earlier as a preliminary exercise, what we did was we collected data. Like the person was told to do jogging, and we collected that data. The person was told to do this activity, and we collected that data. But when we completed that entire pipeline and we saw the real-time classification, we were challenging at that corner because we didn't record the transitions. So for that, what we have done, we have implemented like sync of the radar and camera data. For that, we are asking the person to do any of the 4 activities or all the 4 activities in any order, and we have the camera recording in sync with the radar data. Then we can label the data as per it. So my suggestion is to record the transitions to get the unbiased data.
Okay. One final question, which also I had the same question. So, do you think by Sandeep Mistry? It is. So do you think it would be possible to have the entire system running on Cortex-R, or so rather than the DSP? So whether we can eliminate the use of DSP.
Yeah, that is possible because there is also one more component like hardware accelerator present, so we can do the signal processing on it. And why I'm suggesting to use hardware accelerator or DSP, because these hardwares are programmed in such a way to run the algorithms optimized in an optimized way. So if you don't want to use the DSP, do the entire signal processing on the hardware accelerator and do the classification on the R4F. But in case you want to do everything on the R4F, then you have to see how optimized in how optimized way you can write the algorithms on R4F itself.
Okay. I think yeah. So that was a lovely talk by Radha, and it's promising to know that there are other technologies out there which can replace. Provide much more privacy at the edge compared to like camera or even sound. So yeah. So it's time to thank the sponsors. Executive strategy partners. So here, ARM AI. ARM AI virtual talks. So they discuss the latest trends and technologies and practices from ARM and other ecosystems. Fortnightly, Tuesday at 4 p.m. GMT and 8 a.m. PT. Edge Impulse, the leading edge ML platform. Qualcomm AI Research, advancing AI research to make efficient AI ubiquitous. Sentient, end-to-end deep learning system. Then Platinum Strategic Partners, Deep Light as the fastest video analytics solutions on ARM. ClickerTech, Global IoT Solutions. Reality AI, add advanced sensing to your product with Edge AI and tinyML. Broad and scalable edge computing portfolio by Renesas. Gold strategic partners, FotaHub. Maxim Integrated, enabling edge intelligence. Latent AI, adaptive AI for the intelligent edge. NXP. Seed Studio, deploy tinyML into the real world plug and play ML. SenseML, build smart IoT sensor devices from data. ST, Life Augmented. SynSense builds sensing and inference hardware for ultra-low power embedded mobile and edge devices. And Silver strategic partners, Aeon Devices, EMSA, GreenWaves Technologies, Grow, HOTG, Imagimob, Item Iris, Prophecy, Kixo, Rexen Technology, SAP, Stream Analysts. So don't forget to tune into the next tinyML talk on Wednesday, June 8th by Danilo Pau, ST Microelectronics, organized by the tinyML Meetup Italia. So webcast starts at 8 a.m. Pacific time. And if you're interested in presenting at tinyML or any tinyML talks, so please contact talks@tinyml.org. So thanks everyone for joining and for this talk. See you in the next one.